So I'm going to tell you about a new technique called multipath triangulation that allows a Wi-Fi device to determine another node's location and orientation by overhearing as little as one packet. This work was led by Elahe, who's the first author. Unfortunately, she couldn't be here because of visa issues, so you need to settle for me. This is her primary work lately, so I'm very upset that she couldn't be here to talk to you about it. If you have comments or feedback, contact her directly, email or telephone. This work was done at the University of Virginia. I am currently at Amazon, and we are hiring research scientists. If you are interested or people you know, contact me. So the problem we were trying to solve with this work is called unaided localization, which basically means being able to locate a device just by receiving packets from it. In other words, the ability to unilaterally determine another node's position and orientation by receiving one or more packets from it with no assistance from any other node, not even the transmitter. That's what we call unaided localization. And it doesn't have to be the access point that's locating things. In many environments, like a home, for example, there are often many things in the house that are transmitting to the access point. But if unaided localization is possible, any node that overhears those messages can locate all of those devices. And this would enable a number of new context-based applications. For example, if you asked your smart speaker to show you pictures of Munich, then it could cast that picture to your laptop if it detected your voice coming from the kitchen, because it knows where the laptop is, or to the living room if you're in the living room, because it knows where the television is and what the orientation of that is. So the question we were trying to answer in this work is, could we achieve unaided localization with decimeter-level accuracy with commodity radios? So today there are basically two kinds of Wi-Fi localization that give you decimeter-level accuracy. The first are variants of triangulation. Multipath interference has long been a challenge for triangulation in indoor environments, but recent work, including SpotFi and ArrayTrack, have shown that you can eliminate the multipath interference in order to isolate the line of sight path and better estimate the angles to the target, enabling you to get decimeter level accuracy. But this approach still requires multiple receivers, typically 5 or 6, to get that kind of accuracy. And so they're not doing what we call unaided localization. The next technique is variants of trilateration, which means you need to estimate the distance to the target, not just the angles. And that's much harder. Wi-Fi radios don't have the bandwidth to estimate time of flight with decimeter level resolution. But several recent techniques like Chronos and ToneTrack have shown that nodes can transmit packets on multiple channels sequentially in order to emulate a wider bandwidth and estimate the time of flight. They still need to eliminate multipath interference in order to get decimeter level accuracy. Chronos, for example, is able to use this technique to eliminate the need for a third node by trilaterating the position of the target based on distances to its 3 antennas. But it still requires coordination with the transmitter. And not just to hop between frequencies, but also to estimate the skew between the clocks on the transmitter and receiver. They use the principle of symmetry, much the same way that people use two-way communication to estimate round-trip time of flight. So this bidirectional communication is unavoidable, and the technique can only be used if both the transmitter and receiver are running the localization protocol. And so they're not doing what we call unaided or unilateral localization. And in this technique, in this work, we take a different approach. Instead of trying to eliminate multipath interference, we use it to locate the target. Every reflected path is an independent measurement of the target's location. If we take a reflected path and a line of sight path, we combine those to create what we call a multipath triangle, and we use the geometry of that triangle to locate the target. First, we'll estimate the angle of arrival of the line of sight path and the reflected path. We'll also estimate the angle of departure of those two paths. And these parameters fully constrain the shape of the triangle, but not the size. The triangle can sort of shrink and grow arbitrarily. And at first, it wasn't even clear to us that this technique would work at all. I just explained how Wi-Fi can't estimate time of flight with high accuracy, at least not in an unaided fashion. And we don't know the location of the reflecting surface. So we can't estimate the length of any of the edges on this triangle. The breakthrough was that actually we can constrain the triangle with relative time of flight. So for example, if I know that the path along edges B and C is 1 meter longer than the path along edge A, I've now constrained that triangle size and shape. So it's fully constrained, and we can now locate the position of the target. So we call that multipath triangulation. It uses reflected paths, multipaths, in the same way that conventional triangulation uses multiple receivers. But the two are fundamentally different techniques. Conventional triangulation relies on what we call the well-known angle-side-angle congruency theorem. But multipath triangulation relies on what we call angle-relative side angle. You won't find that theorem in your geometry textbook. The fact that this geometry can be solved and that it enables big practical gains in terms of localization is one of the main contributions of this work. So now let me explain how you would use the technique. I'll do it in two parts. The first is to explain how we estimate the path parameters with what we call 3D multipath resolution. And the next is how to solve the multipath geometry. So as you know, RF signals propagate along multiple paths to get from the transmitter to the receiver. But the receiver can only measure the total sum, the mixed signal from all of those paths. And the goal of multipath resolution is to estimate parameters of the individual paths based on the aggregated measurements that are taken at the receiver. Several algorithms can do something like this today, but nothing can estimate all the path parameters necessary for multipath triangulation. So for example, if you have 3 antennas, you'll get 3 measurements. But in this diagram, we've got 6 parameters, so it's under constraint. So we get around this problem by relying on modern MIMO and OFDM technologies. Every antenna transmits a signal to every receiving antenna, and the radio hardware measures the amplitude and phase resulting from each of those paths, which it provides you as what's known as a CSI value. So for 3 antennas, a 3x3 MIMO scenario, you'd get 9 CSI values. And it also transmits on multiple frequencies. And for each frequency, we get a whole new CSI matrix. So for 3 antennas and 30 frequencies, we get 200 CSI values, which are each an independent measurement of the total sum of all those independent paths. And so then we want to estimate or model how those 270 values will change based on the properties of the propagation paths between the transmitter and receiver. And we do that in terms of 3 properties. The first is angle of arrival. We expect phase shifts between receiving antennas, and that phase shift should be a function of the angle of arrival of the path at the receiver. We also expect for any signal that is transmitted from 2 different antennas on the transmitter that there'll be a phase shift between what's received, and that shift is a function of the angle of departure from the transmitter. And if a signal propagates along, if 2 signals propagate along the same path at different frequencies, we also expect a phase shift between those 2 at the receiver depending on the time of flight or the path length. And so we expect the CSI values to reflect these three different aspects of every path. And now we take these properties and define a system of equations that models how the CSI values will change based on the paths, on the propagation paths. So for example, if the value that's measured at one antenna is some known constant value that we observe, we expect the value to be that's measured at another second antenna to be the same value with some predictable phase offset that's a function of the angle of arrival. And all the values at those three antennas, those three receiving elements, should basically be the same on a different frequency, but again with some phase offset that's a function of the time of flight of that path. And all of those frequencies and receiving antennas should have the same phase offset, but same phases but with a slight offset depending on which antenna it's being transmit from. And so if you have another path, the same thing applies, but you have different values based on those path properties. And we can take all the paths that go between the transmitter and receiver and just add them up, and that gives us some predicted relative phases between the CSI values. So this becomes a big system of equations with the left-hand side of the equation being our CSI values. These are measured observed values. And the right-hand side being the path parameters that we don't know that we want to estimate. And we have 270 such equations. If there's only two paths, we only have 6 parameters, so it's well over-constrained. And we can often estimate about 5 to 7 paths, basically by throwing this into a big nonlinear solver. And then once we have those path parameters, we want to solve for the location of the target. And there are 5 parameters we need to estimate, shown here in red. X1 and Y1 are the location of the target. Alpha is the orientation of the target with respect to the receiver's orientation. And X2 and Y2 are the location of the reflecting surface. So we analyze this geometry and derive 4 equations that define the relationship between the path parameters that we just estimated and these geometric parameters that we want to know. Notice that the last equation here is defined in terms of delta t, or relative time of flight. None of these equations require the absolute time of flight of any path. So these 4 equations can be solved, and you get the orientation and location of the target. So now let's talk about how well this works. So we implemented this system as what we call monolocal. We use commodity Wi-Fi chips, the Intel 5300, which is pretty common in this line of work with CSI values. And we ran multipath localization using the 802.11n protocol with about 40 megahertz of bandwidth, which means that if we were using time of flight, we would have something like 7.5 meters of resolution, so very low time of flight resolution, but still enough to run multipath triangulation. And we executed this in the 5 gigahertz band. We hooked those chips up to a linear antenna array with 3 antenna elements, very similar to what you might get in a standard off-the-shelf Wi-Fi access point today. And we used 2.7 centimeter antenna spacing, which is pretty small. If we use something like a circular antenna array or a larger spacing between elements, it should only improve the results. And then we evaluated this in 4 different environments, starting in a controlled anechoic chamber and moving to more realistic environments in a home and in 2 office settings. And then finally in a very large, cluttered environment with narrow corridors. And these areas ranged from on the order of 4 by 7 meters to 9 by 14 and as large as 16 by 25 meters. And these cumulative error distributions here show that the median error was about 50 centimeters in the main environments, degrading to about 1.3 meter median error in the worst, most cluttered environment. And that orientation error, which means how accurately we can estimate the orientation of the transmitter, the median error was about 10 degrees or lower across all of the environments. And if you transmit more packets, if you receive more packets, I should say, the error does go down. But this graph shows that we're getting a median error across all environments of about 80 centimeters with only 7 packets. And you get diminishing returns beyond that. So one of the reasons why this works is because the 3D multipath resolution algorithms that we developed are able to estimate angle of arrival and angle of departure better than other approaches. These angles are essential for doing localization. These graphs here show that the angle estimates were about 5 to 10 degrees more accurate than state-of-the-art. And we know this because these studies were done in a controlled environment in an anechoic chamber, so we could actually control where the reflecting surface was and what those angles were. So to conclude, this work has 3 main contributions. The first is what we call multipath triangulation. It's a new localization technique, and the first one that can achieve unaided localization with only relative time of flight values. It's a general method, and it can be applied well beyond Wi-Fi, basically to any hardware that doesn't have the capability of measuring high-resolution time of flight, which essentially includes almost all commodity radios today. We also proposed a 3D multipath super-resolution algorithm to estimate properties of individual paths. And this technique can simultaneously estimate more parameters and achieve higher accuracy on those parameters than state-of-the-art multipath resolution techniques. And then finally, we implemented this system in what we call monoloco. And basically to show that this technique works on commodity hardware today. And presumably the results might get better with future versions of hardware that have, let's say, lower phase noise. And this implementation is, in fact, is the first Wi-Fi localization system that simultaneously provides decimeter-level accuracy, location accuracy, and degree-level orientation. And it does that using only a single receiver, single carrier frequency, no coordination with any node, including the transmitter, and receiving only a handful of packets. So that's it. Thank you for your attention, and open to questions.
Thank you, speaker. Any questions? No questions?
Hi, Karthik from University at Buffalo. I didn't quite get, so you had the math for a single multipath effect, right? But in the real world, there are likely many multipath effects, and the bigger challenge is you don't know how many, right? So it's not easy to figure. So I'm not sure how in the corridor office scenario you were able to estimate these things similarly. I didn't quite get what you did for many multipaths.
If there are many multipaths, is that the question? I'm not sure I understood the question, but I think what you're asking is, if you have a lot of paths, can you still estimate? So I explained the models in terms of 2 paths, but if you have more than 2 paths, you would just have more terms. Let me pull up the right slide. You would just have more terms in your system of equations.
Right. So, no, but the question is, how do you know how many, right? So the challenge is, so you can do the math, it's a very over-constrained problem, so you can solve for different paths, but you don't know how many, right?
Oh, if you don't know how many. Yes, so you do need to solve it for a certain number. Generally, we don't actually care. So if you solve it for 3 or 5 or 7, most of the results here are based on the first 2 paths anyway. Often the first path, the line of sight path, is the clearest. The second path is the second clearest, but beyond that, they start to get more noisy than the first 2. So you can still pick them up, but they're noisier. And so using them for localization often doesn't improve your performance and may even actually make it worse. So we generally just use the first 2 anyway. Good question.
So if I could add on to that question, so because your results do show that when you're in this big public area, then the performance is worse, right? So one apparently it could be that you just have more multipath, have a more complicated multipath scenario. So in that case, would increase this number of paths you consider help at all, or it's probably just too noisy for you to even add any new information?
It's a good question. We can only hypothesize why we get worse results in the more cluttered environment because we don't have ground truth on where the paths are actually reflecting from. Only in the anechoic chamber do we have ground truth. We suppose that it's because the tables were about the same height as our radios, and so our line of sight signal was probably attenuated much more in that environment than in some of the other environments where, yes, there's clutter, but it's not necessarily blocking the line of sight. So that's what we expect, but it's not entirely clear. It may also just be because of the larger area, and we're talking about longer distances. And of course, if you have angle error, a constant angle error translates to a larger position error as you get farther away.
I have follow-up questions. So after you solving these equations, how do you determine which path is the best path, which path is the second best path? Because after you're solving these equations, you only got the phase information of each path, right?
I see.
Yeah.
Right. So I was ordering the paths. So this system of equations is a nonlinear system, and you can solve it with a whole bunch of different approaches. We happen to use MuSiC, which is a common super resolution algorithm, and it gives you essentially an energy value for each path. So you have a pretty good idea of which ones are the strongest, and we end up using the strongest multipath reflection, and we also use the path that looks like it's probably the line of sight path because it has the shortest relative time of flight value.
Luca De Mori from Sorbonne University. I would like to ask, probably I missed it, but do you need line of sight to implement this method, or? You
do need a line of sight path.
Yeah, that's.
And so does every other localization algorithm out there. Okay. It doesn't necessarily need to be line of sight in the sense that it's unattenuated. It can still actually be a weak signal. So it can go through a wall, for example, but you have to at least pick it up so you can estimate the angle of arrival, time of flight or relative time of flight, and angle of departure.
And then how can you be sure that you have, okay, you can measure it, so you think, you say, okay, I took the first one that I got, but are you always sure that you can say that that is the first, that is the line of sight? Do you have some way to recognize that you have line of sight or you don't have a line of sight?
There are ways in theory because you have an over-constrained system, and so in theory you would be able to figure this out. But in practice, it's very hard because you have a lot of noise. As far as I know, every localization system for indoor localization requires a line of sight path, and nobody has a technique to guarantee or eliminate cases where you don't have one. That may, in fact, be one of the explanations for why in an environment where the radios are the same height as all of the tables and chairs, we end up getting higher error because maybe we're missing the line of sight path in some cases.
Okay, let's thank our speaker.
Okay, thank you.